So this will be a survey talk about sparse partitions. It's somewhat longer than the other talks. And let me also tell you that actually all the morning sessions is kind of about sparse partitions, also the two following talks. And my plan is basically to tell you about sparse partitions, mainly show you some cool algorithms and applications. Towards the end, we'll also show you how to construct them. And before I define them, let me start right away with some application of them. So recall the traveling salesman problem. Here you have some metric space X, and given some subset S of points, the goal is to find the shortest cycle toward the traversing all the points in S. So this is a known and beloved problem. However, suppose that you need to solve this problem repeatedly. For example, you're a postman, and you have this bunch, all the metric points are all the potential places you want to visit, deliver post. And each day at morning, you get the subset of the places you need to go through, and you need to decide how to go. So you can compute each day TSP or approximate the TSP from scratch. This time consuming, it's before your morning coffee. And you prefer something easier to decide how to go and where to proceed. So a different solution will be a universal TSP. So this is a single tour traversing all the metric points. And once you are given a specific subset of points that you need to deliver them all today, you simply go in this order, that is making all the shortcuts on the universal tour. And so this is the universal TSP. This is for every subset, there's induced solution. And the performance of this universal TSP, which we call stretch, is simply the worst possible ratio between the induced TSP tour and the optimal solution. So here this red versus the blue. So quite surprisingly, it's possible to achieve something reasonable with the stretch parameter that is fulfilling all possible subsets in the same time. And as was shown by G et al., this is a meta-theorem saying that if your metric space admits a certain sparse partition with parameters sigma and tau, which we soon define, scheme, then there's a solution to the universal TSP problem with stretch which is polynomial in these parameters times log n. And as we will show, there's indeed good sparse partitions, logarithmic parameters, and therefore there is a universal TSP tour with polylogarithmic stretch. So let me briefly mention that actually the state of the art is log square, but we don't care about that because this is talk about sparse partitions and not universal TSP. Okay, so let's define this mysterious sparse partitions. So this is a deterministic, in a sense, creature. It's just single partition. And there's three parameters, sigma, tau, and delta. And we said that this partition is sparse if. So this is like a partition. And then it's sparse if first, the diameter of each cluster is at most delta. And secondly, every ball of radius delta over sigma intersects its most tau clusters. So this ball here intersects two clusters. This one intersects three clusters, and so on. Right, so there are three parameters. Delta is the scale parameter, the least important one. Then sigma we call the padding parameter. This is historical reasons, but basically this is the ratio of the radius of the ball that you fulfill. This is supposed to be larger than 1. Right? This is smaller, obviously, than the diameter, usually larger than 2. And finally, tau is the sparsity parameter. This is the bound of the number of intersections that each ball will have. Yeah, and we say that a metric space admits sigma tau sparse partition scheme if you have such a sparse partition for every possible scale delta. Yeah, and the theorem by G et al. Was that if your metric space admits a sigma tau sparse partition scheme, then you have a solution to the universal TSP problem with a stretch which is a function of sigma tau and log n. Okay, so let's see the algorithm. It's very cute, so I'll show it, not prove it, but the algorithm is super cute. So this is your metric space. And at first, you create a sparse partition with some small scale delta 1. Now this is your partition. For every cluster, you choose some representative. And you add edges from all the vertices in the cluster to the representative. Next, I keep only the representatives. And I will again compute a sparse partition, but now with a larger scale delta 2. Right, and again, I choose representative from each cluster. I'm adding edges from the vertices in the cluster of the representative. I keep only the representatives. I compute a sparse partition with larger scale, choose representative, add edges, keep representative, and finally I get a single cluster containing all the remaining representative, and the algorithm stops. So if you go back, what happened here is that we created a tree over the metric space. And the universal TSP will simply be a DFS tour of this tree. Simply go in some in order or something, and this is your universal TSP. So quite elegant. Yeah.
Question.
Yeah.
So as you thin out the metric space, so you're finding sparse partitions in the smaller metric space then, in the
I mean, you can
look,
you can construct sparse partitions of the original metric space and take the induced partition. You still have all the guarantees.
I see.
Yeah, and the theorem is that this universal TSP has stretched out times sigma square log n. So I'll briefly maybe tell you some idea of why it works. I will not prove it, but just to get some small intuition of what makes it tick. So consider some scale delta that somewhere in the middle of the algorithm we constructed sparse partition. The subset actually is not very important which subset do you choose, because I mean this is completely oblivious. You just take sparse partitions of the entire space. I mean there's something in the argument, but we'll ignore that. Suppose you just want to show that this thing is a good TSP. And consider a set n, which is a delta over sigma net, which is simply a maximal subset of points at a pairwise distance, at least delta over sigma. So this is this red points here. And that means that if you will take balls around these net points, that every ball will contain single net points, and every point will belong to some ball, right? Because it's a maximal subset. And now, if you look on optimal solution on the entire metric space, then it must go over all the net points. Going between any two consecutive net points will cost you at least delta over sigma. So the overall optimum is at least the number of net points times delta over sigma. This is from the one hand. From the other hand, let's compute how many edges. I mean, in the TSP, in this kind of DFS tool, we have this tree, and there's log n levels in a sense. And let's consider a single level and compute how much you paid for this specific level, which is at scale delta. Right? So the number of delta level edges is bounded by the number of clusters in this partition Pj at this level. But the number of these clusters is obviously bounded by the number of intersections of these balls with the partition. I mean, because it's actually much larger, but it's bounded because I mean every point belongs to some ball and contributes some intersection. But each such ball could intersect only tau clusters. This is by definition of sparse partition. And therefore, the overall number of clusters at this level is bounded by number of net points times tau. And now if you want to know how much you paid, so this will be simply the number of edges times delta. This is what you pay for each such edge, which bounded by here by the number of net points times tau delta. But recall the optimum is kind of a function of delta times n. So you can replace it here and get some bound on the optimum. This is more or less the main idea. I will not go any farther than that. And as we said, this has a small stretch, this universal TSP. OK. So this was the first application. Let me right away move to the second one, which is looks completely different. But it will go back to some version of this sparse partitions. And so this is a Steiner removal problem. So I'll kind of lie a bit about the definitions to simplify it. But the main idea in the Steiner removal problem is that you have some metric space. Consider you have a planar graph, and you have k terminals. And now you want a graph which will be planar only on the terminals. And you ask, what is the best possible stretch that you can get? So we'll use this definition. You have a graph G, and you have a terminal set K of size small k. So this is like the graph, and the big vertices are the terminals. And now the goal is to find a partition such that each cluster is connected and contains a single terminal, like this partition here. And now if you contract the edges of each such cluster, you'll get a minor of the original graph. And the weight of each edge will simply be the shortest path in the original graph. And this is that if you start from a planar graph, this will be a planar graph. And yeah, this is the weights. And what you try to minimize is the distortion, which is the ratio between distance in the original graph between two terminals to the distance in the minor. And in this example here, so between T1 and T3, originally it was 4, now it's 12, so the stretch is 3. Right? So the problem is basically, to find these good partitions such that the induced minor will have small stretch. So what is known about the problem? So the problem was started with trees, where Anupam showed an upper bound of 8, and Chan et al. Several years later showed that it's tight. On general graphs, we know an upper bound of log K. Recently, there's a lower bound of squared log K, so there's only a quadratic gap. But actually, the problem is most interesting on planar graphs, because I want like a minor which will remain planar, and this was open for a long time. And the recent attack on this problem was to like a meta theorem in the spirit of J et al., which tells you that if every subgraph of G admits a sigma tau scattering partition, which we'll soon define, some version of sparse partition, then there is a solution to the Steiner point removal problem with distortion, which is a factor of these two parameters, sigma and tau. Okay, so again, the same meta theorem. So now if you can show that every planar graph admits this type of scattering partition, then you will solve the problem. So what is scattering partition? So now this is a problem on graphs, and not on metric spaces, as was the problem before. So in particular, we want the partition into clusters of diameter at most delta, but we also want these clusters to be connected. Well, previously there was no graph, so no connectivity. And secondly, instead of balls, we're looking now on shortest paths. So we said that this partition is scattering if every shortest path of length at most delta over sigma, previously it was radius delta over sigma, intersect at most tau clusters. So this shortest path here intersect 3 clusters, this one intersect 4, this one even 5, but yeah. Basically, we want that every shortest path intersects a small number of clusters, and then again, 3 parameters. Sigma, so here sigma is usually just 1, because you can concatenate paths, it's not really important. And the important parameters is number of intersections, and scale, again, is not super important. And we say that graph have a scattering partition scheme if you can construct such scattering partition for every possible scale delta. And the theorem that if you have such a scattering partition for every subgraph, then there is a solution to the Steiner point removal problem with distortion, some poly sigma tau. Okay, so let's see the algorithm, which is again super cute. So I remind you, in the Steiner point removal problem, the goal is to find a partition into connected clusters, such that each cluster contains a single terminal. So these colored vertices here are the terminals. And similarly to the previous algorithm, I begin by constructing some scattering partition for some small scale delta 1. So this is the partition. Now, every cluster which contains a vertex, which is a distance about delta 1 from a terminal, will be now clustered or assigned to some terminal. Right? So all these clusters here will be assigned, and I kind of decided for them to which cluster you will belong eventually. And all the other vertices are undecided. Now look on all the remaining vertices on the induced graph on them, and then compute a scattering partition with a bit larger scale, delta 2. No, it's this one. And again, every vertex, every cluster that contains a vertex, a distance at most delta 2 from some terminal, will be clustered. So it's these vertices here, and again, now we do it with slightly larger scale. However, so all these vertices, so actually here, all the clusters other than that one should be assigned. However, previously it was clear to which terminal you should go, but now it's not super clear. So this cluster should become orange or green. So the way we resolve these issues is by constructing a super graph, where each clusters have a single representative, and we have an edge between 2 clusters if there's an edge between vertices in these clusters. And this is an unweighted graph. And every cluster that I decided that should be assigned will simply go to the closest terminal, breaking ties some arbitrarily fashion. Right, so this is the solution here. This is the clusters. I run the another layer, and everything is decided. And this is the partition. Right, and once I have the partition, the Steiner part removal problem have this induced minor. Okay, so let's see why this thing, this has a small distortion. Let's see why this thing works. So again, I briefly tell you some idea. I will not go too deeply into this proof. So consider a pair of terminals, this green one and the turquoise one. And this is the shortest path between them. And consider some scale delta when I constructed some scattering partition. As a result of the scattering partition, the clusters were assigned to different terminals, right? I have the supergraph, and every cluster that is close enough to a terminal assigned to a terminal. And suppose that this cluster been a distance 2 from here, and I guess should have gone to here, but never mind. And as a result, I will cluster them, and eventually my graph, my minor, will contain only the terminals. So the way to go from the green to turquoise will go to first the purple, because this is like, I'm trying to go along this red path, and each time some vertex here is taken by some other terminal, we'll go and visit this terminal, and I'm going here, and then eventually I will go to the turquoise one. And this, in a sense, induces you some detours, right? So instead of going on the shortest path, I'm having a detour now to here, and then a detour now, and then you go back to the red path, and then you go have a detour to the orange path, and then you go back, and then to the turquoise, and so on. And what you will pay for this, for the scale delta at least, is the number of detours times the length that you pay for each detour. Yes, so, but the number of detours is bounded by the number of intersections of your path pi with relevant areas. I mean, it might be very long, much larger than delta, but essentially the number of detours is bounded by the number of intersections. And each detour will cost you about delta. Right? And because the number of intersections is bounded, so overall this is somehow works.
So how don't you pay for the number of scales?
Because, this is geometric series somehow. And, only the important scales, in a sense, really matter here. You can't think that you partition the path into like chunks where each chunk is kind of accordingly to the distance to the closest terminal, and you will pay for this chunk the detours which are proportional to this distance. Yeah.
And how related to planarity?
This doesn't relate to planarity.
No, but you said it.
No, the application, if you can do it for planar graphs, then it will be great.
So can
But
you
the theorem, you should wait a bit. Yeah. Right. So the theorem that if you have such scattering partition scheme for every subgraph, then your specific graph have a good solution to the Steiner part removal problem. Right. So back to Yuri's question. So what about planar graphs? And at this point, I will be very happy to tell you that there are scattering partitions for planar graph, and therefore everything works. Unfortunately, this is actually still an open problem. However, don't despair. The situation is not that bad. And recently there was a very exciting developments by Chang et al., who defined a relaxed version of scattering partition that they called shortcut partition. So there are some differences, but morally the main difference is that while in scattering partition you should satisfy every shortest path, in shortcut partition you just need to satisfy a single approximate shortest path. And you can show that if you satisfy a single approximate shortest path, then the argument that I gave you previously actually still works. This is good enough. And they showed that planar graphs, and they showed this a similar meta theorem that if every subgraph submits a shortcut partition scheme, then you have a good solution to the Steiner removal problem. And most excitingly, they show that every minor free graph, even stronger than planar, admits a shortcut partition scheme with the parameter is just some exponential in the minor r. And therefore now, we have a solution for the Steiner part removal problem for minor free graphs, and in particular for planar. Okay, so actually they have several further applications for their shortcut partition. This is not a meta theorems in the spirit of this talk. Not really delve into it, but there were like tree covers, which means that you They use it to show that every minor tree graph, you can construct a small collection of trees, that every pairwise distance is well approximated in one of them. And actually for planar graphs, only epsilon cube trees are enough, which was very surprising. And there are also decent circles and some additive distortion embeddings, but yeah, I'm happy to tell you about it later. And now we'll move to the next problem, back to sparse partitions, which is a universal Steiner tree problem. So consider the following scenario. You have some big network, and you have some single server, and many clients. And at some point, the server wants to send some message to some subset of the clients. And the server will pay for sending the message according to the total weight of the edges that he used to send the message. So given that specific instance, the optimal solution is simply the minimum Steiner tree. However, suppose that the server needs to send these messages repeatedly, or maybe he wants to construct some like hardware network to send these messages, right? So he don't want to compute each time from scratch a Steiner tree. So a different solution will be a universal Steiner tree, and this is another example. A different solution will be a universal Steiner tree, which is a single tree over all the points of your graph. And then, given some specific instance, you will simply send the message in the induced tree. Now there's only a single solution, very easily computable, the green tree here. And now when you have a new instance again, you will simply send according to the induced tree. And similarly to the universal TSP problem now, the stretch of this tree here is simply the worst possible ratio between the cost of induced Steiner tree to the optimal Steiner tree. And back in the same paper in 2005, Jet al showed that if G is a metric space or a complete graph, then which admits a sigma tau sparse partition scheme, then you have a good solution to the universal Steiner tree problem. Right? So the caveat here is that it works only for metric spaces. And if you want you have a graph and you want your universal Steiner tree to be a subgraph, this tells you nothing. Right? And back, from here you can know that every complete graph have a universal Steiner tree with stretch point logarithmic. And 7 years later, Bush et al. Showed a similar meta-theorem, stating that if your graph admits a gamma hierarchy of strong sigma tau sparse partitions, we'll define it soon, then there's a good solution to universal Steiner tree with stretch, which is some function of this sigma, tau, and gamma, times log n. I think I have a missing slide. Probably it comes later, actually. OK, let's continue with defining these sparse partition schemes, and then maybe I'll tell you what they proved. So recall a sparse partition have 3 parameters, sigma, tau, and delta. And need that every cluster will have diameter at most delta, and every ball of radius delta over sigma will intersect at most tau clusters.
Question.
Yeah. Just a question on this universal Steiner tree.
Yeah.
Maybe I missed this. So this like special node that you mentioned, like this orange node in this diagram, are you guaranteed that that's always going to be one of your?
Yeah. No. Every tree should. This is like the important point you always might contain it. Without this kind of server point, red point, it's impossible to solve it, because they can't just give you an edge, and then you cannot cover everything. Yeah, this is important for the problem. Thank you for the question. So this was a reminder for sparse partitions. And now I want a gamma hierarchy of strong sparse partitions. Okay, so first, let's understand the word strong. So previously, sparse partitions were defined on metric spaces. Now we define it on graphs. So instead of just diameter delta, I want that the strong diameter of every cluster will be at most delta, which means that if you look on every cluster, the induced subgraph on the cluster has diameter at most delta. This is usually what you need when you work with graphs. And now I want a gamma hierarchy. So this is instead of a scheme, a hierarchy, which means that I want a laminar partition, so first partition, second, third, and so on. And each partition will refine the one after it. And you have this gamma parameter and every like partition will be sigma tau gamma to the I parameter. So gamma is a parameter that tells you the difference between two consecutive scales in your hierarchy. So suppose that, for example, this is your graph. So this is like the first partition with very small scale, gamma. And then you have a larger scale, gamma square. But this should be a coarsening of the first partition, and so on. Right now, the blue one is like a coarsening of the second, and so on. And what Bush et al. Showed, that if your graph admits a gamma hierarchy, so previously you need a scheme for every possible scale. Actually, gamma hierarchy was good enough, but gamma hierarchy is means stronger because now it's a hierarchy. You refine each other. So if you admits a gamma hierarchy of strong sigma tau sparse partitions, then there is a solution to the universal Steiner tree with stretch polynomial in sigma tau and gamma times log n. And what Bush et al. Showed is that every graph admits 2 to the square root log n hierarchy of strong to the square root log n to the square root log n sparse partitions. And using their meta theorem, you can conclude that every graph admits a solution to the universal Steiner tree problem with stretch 2 to the square root log n. And the only lower bound was log n. And in the last year, we proved with Bush and friends that every graph admits a log square hierarchy of strong log n sparse partitions. And I would like to tell you how we got that. Okay. And as a conclusion, you will get a logarithmic stretch for the problem. Okay, so first I'll begin by showing how to construct sparse partitions in general, and then we'll discuss how to make them into hierarchy. So for this, I'll show you my favorite algorithm, the Miller-Peng-Chu algorithm, which is a clustering algorithm with exponential clocks. So here you have your graph, and there are some terminals. And think that every terminal have some waking up time, which is like 4, 2, 1, and 4. And this is a clustering algorithm. So you think that there's like a time scale, which starts at minus infinity. And when there's a time coming to minus your waking up time, the terminal wakes up and start to creating its cluster in like a Dijkstrom fashion. So at times minus 4, these two terminals wakes up and creates a clusters containing only themselves. And then next time step, they will increase their cluster by a single step, while these two are still asleep. The next step, these two are increasing by 1, while the second terminal wakes up. The third one is still asleep. Then with the next time step, this one wakes up, all these are grew, and then we continue until everything is clustered. So formally, this is defined as follows. So for every terminal, you have some waking up time or shift. We call it shift, delta t. And for every vertex v, there's some function over the terminals, which is the shift minus the distance to the terminal. And v will join the cluster ct, which maximizing this function. So if delta t was 0 for all the terminals, this will simply be a Voronoi partition, which means every vertex goes to the closest terminal. But now what we have here, in a sense, is a shifted Voronoi partition, when for each terminal we get some, like, we try to help it in some way, but each one have some different help. So you can think that you start with a Voronoi partition, but usually Voronoi partition is a very bad solution for problems, and then you smooth around the boundaries of the different clusters, you get something nicer. Another way to think about it, so we will sample this delta t's using exponential distribution. So you can think that, like, eventually, for the vertex v, decide to which terminal it will join. So all the terminals like start in their distance from a terminal, and then you start to sample this exponential distribution, which is like memoryless. So like you're tossing coins, and they're all continuous. So it's kind of a race of who will survive last. And the one who survives last, this will be the terminal to whom cluster I will join. And we'll discuss it again soon. Yeah, and the algorithm simply, as I said, samples these shifts using exponential distribution with parameter delta over log n. Yeah, so delta is the kind of the diameter of the clusters you're aiming for, and the noise here parameter is very small. It's only delta over log n. Okay, and the theorem is that this algorithm actually achieves a log n sparse partition with high probability. So so let's see why it works. So consider like your graph, and these red points are the terminals, and this is your vertex v, and this is a ball of radius delta over log n around your around your vertex v, and you sample these shifts around terminals. So the kind of performance of this terminal t is it shifts delta t minus the distance to the terminal, and the vertex v will join the terminal that maximizes this function. Right? So as I said, it's kind of a race. Right? So you can think that every terminal starts at some point, and then you toss coins until you get some tail or something, and you stop. And this is kind of the final position. So this terminal T1 is the winner. It's the one who got last, right? Maximize its function Fv. And T2 is the second best, and T3 and so it's the third one, and so on. And the point is that if you look on the vertex like U, which is very close to V, this race with respect to is not very different than the race with respect to V, because the only things that change is this distances, but the distance between V and U is like very, very small. So if a vertex U from this small ball join the cluster of some terminal T prime, it means that T prime was almost a winner also in V. Maybe it's not the winner, but it's almost a winner. So we say that the vertex is almost winner for V if it's like this difference from the winner is most this delta over log n. And we can show that all the vertices in this ball join to almost winners. Okay, and now because of the memories properties and like we toss these coins and everything moves, so we can show that the number of almost winners is only log n. Okay? And the conclusion is that the number of clusters intersecting this ball is only log n, because it's only clusters which centered in almost winners. Yeah? And these all clusters are of course connected, so it's a strong log n sparse partition with high probability. Okay, so this was MPX, and yeah.
So, can you say again how the algorithm depends on delta?
Delta is the noise. In a sense, you can think that like once if you have like the argument that if you look on log n terminals, the probability that no one of them will survive for delta over log n steps is kind of almost zero. So this is the reason there's only log n almost winners.
The random variable depends on delta. The random variable, the exponential clock, has parameter, I don't know, what is it, delta or delta over again?
This was the question?
Yeah.
Delta, yeah. I mean, this is just a scale. You can think that it's 1, and then you multiply by delta. It's the same thing. Okay, now our goal. So this is all we know like 4 years ago, and we've been stuck of how to make it into a hierarchy, which surprisingly is very easy, but took some time to see it. So I remind you now I want to construct a hierarchy of strong sparse partitions. So I want a hierarchy so that each partition in the hierarchy will be log n sparse, and they will refine each other. So we'll do it bottom up. So we start like from vertices, and then we construct a partition with scale gamma to the I, and so on, going up and up. So we'll consider a single step in this construction. So your input, in a sense, is what you constructed in the previous step, which is a log n sparse partition with diameter gamma to the j minus 1. And what you want to output is a coarsening log n sparse partition with diameter gamma times j, a gamma to the power of j. And so this is the partition you got. And you need to find a coarsening partition that in the same time will be sparse. So we'll do it in 2 steps. In the first step, we simply run the algorithm that we just discussed, the MPX, with these shifts and this race and almost winners and all these things. And we get ourselves a sparse partition. However, we completely ignored the input. So it will not be like refinement. Like it will not be a coarsening of the previous partition, right? They do not agree. And in the second step, we need to round up this MPX partition that we got with respect to the input partition of the previous scale. And so we'll do it as follows. So first, we hang imaginary centers above K. So recall I told you that MPX is basically a Voronoi partition when you help each terminal somehow with some shift. So what you can do is simply add imaginary terminal above each terminal, which means like you add a single edge. And you can choose this distance here such that the solution of the MPX that you already computed will be a real Voronoi partition with respect to the imaginary terminals. So you just can hang each one in the right distance, so that now the partition that you already computed is exactly a Voronoi partition with respect to these 4 imaginary terminals. Next, we use a procedure which is called cluster aggregation, which basically rounds up Voronoi partitions. So we improved these parameters over the previous papers, but this basically was already known up to the exact parameters. So what is done here is that you give them some Voronoi partition with some terminals, and this cluster aggregation rounds up the Voronoi partition such that each vertex is sent to a terminal a distance at most log n times delta larger than the closest terminal originally. And now it will like respect, so in a sense you get a partition with diameter delta, you get some Voronoi partition which is unrelated to the partition you got, and this procedure rounds this thing up, and like such that like it will respect the original partition, like here. You got something in general, like you have a Voronoi partition, and you have some partition of radius at most delta, which is gamma to the j minus 1 here, and this cluster aggregation rounds this thing up, and the noise in the sense of this rounding up is only additive. This is the important point. It's not multiplicative, but additive, and the additive parameter is log n times delta. So which means that like this vertex here, originally it was turquoise, but now it was now it's orange, and distance from here to the orange terminal is at most log n times delta larger additively than the distance to the closest terminal, which is the turquoise one. Right, so this is the cluster aggregation, and once you pick gamma to be large enough, you can say that okay, now you had some vertex, and it moves to a different terminal, but this difference between these two terminals is only log n times delta. And if this like gap is large enough, so it will be an almost winner. Right? So if you think, so previously I told you there was a race. This was the winner with respect to the Voronoi partition. Sorry, with respect to the MPX. But now we hang these auxiliary terminals. So this is still the same. But now it's not like this function FV, but it's actually real distances to the imaginary terminals. The number of like, and you will go to an almost winner because I mean I choose this gamma large enough, so it kind of eats this additive parameter here. Right? And now look on the ball of V. Now every vertex here go to an almost winner of itself. So consider vertex U here. So now U, instead of going to the supposed, instead of going to the winner, it might go to an almost winner. But almost winner of U is an almost winner of V. Right? So I mean, if before that I look on the gap of like the winner minus this parameter here, now there's two parameters here. Like first, you're almost winner because of the ball, and second, the almost winner because of the rounding up procedure. But it still works because also the number of almost winners is only log n. Right? Basically the same arguments, and that's that. Now you get the corresponding partition with the right scale, like which is log n, and the scale is just gamma to the j. And the gamma you need for this to work is just log square. So this is the gap between consecutive levels, and the conclusion is that the stretch is polylogarithmic by the meta theorem of Bosch et al. Okay, so yeah, let me wrap up. So in the survey talk, I showed you several meta theorems, which tell you that if you have a certain sparse partition scheme, or maybe hierarchy, or this shortcut, scattering, whatever, all these different forms, then you get the desired construction that you want. and this is very nice. We had sparse into the usual TSP, and scattering and shortcut into Steiner point removal, and there's this gamma hierarchy into universal sign tree. Okay, there's a bunch of different partitions of different types that we already understood. So in this talk, we discussed this sparse strong with parameters log n, log n. Also this shortcut partitions by Chan et al, getting this time punchable problem. In the next talk, you will hear about efficient sparse partition for Euclidean space. So actually, I mean, originally in 2020, we already knew how to get this, but inefficiently. This is now efficient in streaming. Yeah. So there are some questions. One question is that actually scattering partitions is still open. I mean, we don't have the application, the cool application now because kind of shortcut partitions solve it, but the shortcut partitions are much more sort of costly. So if you will be able to construct scattering partitions of the same scale, it will improve dramatically the parameter there. Yeah, but it's not as exciting as it was. The universal Steiner tree problem is still not perfectly understood. So this is the situation. We have, this was the previous work on general metrics. Now in general graphs, we have much better understanding. Our upper bound is log to the 7. This is what I showed you today. But the only lower bound is log n. So there's still a polynomial gap between the upper and lower bounds. And interesting case is planar graphs. So actually in the original paper in 2012, Bush et al. Get some polylogarithmic stretch for planar graphs. Now our stretch for general graphs is better, but we actually don't know anything better for planar graphs than what we know for general graphs. Well, it probably should have some better partitions and better solution.
Is there a lower bound for planar graphs?
So yeah, there's a lower bound of log n, I think, over log n. And also sparse partitions. This one is optimal also for planar graphs. But maybe somewhere in the, like you need smaller gap maybe, or maybe just not using a meta theorem, but a direct solution could get you better parameters. Yeah. And finally, about this cluster aggregation problem that I don't really went into, but we have this additive stretch parameter that we get. So the original work had log square. We got log n. And we have some unpublished lower bound of log n. But basically, there's still an exponential gap between lower and upper bounds for this specific problem. That's that. Thank you.
So you think sparse partitions are strictly stronger than scattering partitions?
I mean, you have two types, strong
Let's
and
say
weak.
defined on graphs.
So if you define strong partitions, that obviously yes, because every ball contains the pads.
Weak, yeah.
No, but weak partitions, scattering partition, actually not comparable. Because we have weak partitions for minor free graphs. Sorry, no. No, I'm not sure it's true. But we have weak partitions for minor free graphs, for example. Very good partitions, just based on Pauli decomposition, basically. But we don't know anything scattering about them.
So did you say the sparse strong, like log n log n, there's also corresponding lower bound for planar graphs?
This even for trees hold.
Um,
No, not weak, sorry. The strong
Sparse.
lower bound,
yeah.
long sparse, if you want strong sparse partitions for trees, this lower bound hold.
And you're expecting, or where it's right now open, whether or not there exists O1 scattering partition for planar graphs.
I mean, yeah, if you have like some scattering partition with constant here, yeah, it's open for planar graphs. And anything which is better than that, actually.
Other questions?